Okay, one more minute, then I will start the introduction. Okay, I will stop share my screen. George, please, you can share yours. Yeah, great. So hello, everyone. Welcome to the Magnetosphere seminar series of today. I'm Marco Silveira, and before we begin, I'd like to remind you that this presentation is being recorded. So keep your microphone on mute and send your questions in the chat box. I will read them at the end of this presentation. So today we are delighted to have Dr. George Hospodarsky as our speaker, talking about search coil magnetometers. Dr. George is a research scientist at the University of Iowa with over 28 years of experience in designing, testing, calibration, operation, and analysis of scientific data from radio and plasma wave instruments and sensors flown on spacecraft, including the Cassini, Juno, Van Allen probes, Galileo, and Polar missions. He is responsible for search coil magnetometers development, performance, and calibrations for Polar, Wind, Juno, Van Allen probes, and tracers missions, and the Viper's sounding rocket. His research is mainly on the radio and plasma waves found in the magnetospheres of the outer planets and the Earth. The areas of interest include wave normal and Poynting vectors analysis of the Whistler's mode waves and their relationship to energetical particles. So please go ahead, Dr. George.
Thank you very much. As was introduced, I'm George Hospodarsky. I'm a research scientist at the University of Iowa. This picture I'm showing here is actually for the Viper sounding rocket search coil, which we just recently delivered to Berkeley, and it's supposed to be launched from Wallops in May, hopefully. And, you know, I have my space cap mask on for COVID, you know, just because it's the times. Slides seem to want to be slow to advance. These are just some pictures of the various loops and search coils I've been involved with since I've been at the University of Iowa. The top left is the polar loop antenna. The middle panel here is the Van Allen probe search coil, and this is me and Scott Bounds doing a test at Applied Physics Lab. The Viper search coil again, the Juno search coil and the wave instrument, and the electric antenna preamp. This is the Juno preamp, and this is a picture I just found last week of me that looked like it's rather dated and stuff, but I'm holding up the polar search coils, and I was much younger then, much younger then. And you can't build anything for space without a great team, and so I've tried to list the people I've worked with over the years that I could think of, and I know I missed some people, so I apologize in advance for anybody I missed, but we have a great team, and we've had great people here at the University of Iowa over the years, and I want to thank all of them, especially Professor Gurnett, Bill Kurth, Craig Kletzing, and Roger Anderson, John Bunnell, who's actually at Berkeley, but for allowing me to build search coils for them. Just a brief outline. I'm going to talk a little bit about the motivation, why we like to do wave magnetic measurements in space, and why we use search coils primarily to do this. a little bit of a history of space-based time varying magnetic field measurements, a little short overview of search coil basics, some things we run into when we try to test search coils in the lab, and also when we put search coils on a spacecraft, what we have to think about, and then a little bit of search coil science that's been done, really brief. So motivation, why do we want to do wave magnetic measurements in space? And this is a quote from Don Garnett's chapter in the Measurement Techniques in Space Plasma book, which I encourage everybody to read because they're just full of great chapters about different types of instruments. But he had the plasma wave chapter. Plasma waves play a fundamental role in the physics of space plasmas. And for one example that's used all the time is the wave particle interactions in the radiation belt, especially chorus waves. And I list just 3 papers that summarizes some of the plasma waves. Shahan paper from 1979, the Thorne one talking about the radiation belts. And then I wrote a sort of summary paper in 2012 talking about plasma waves at Earth, Jupiter, and Saturn that we've observed. And my paper especially is just good for references because I tried to reference everything I could find at the time. Wave magnetic magnetometers allow determination of a variety of parameters of the waves. The most basic is, of course, the ratio of the electric to magnetic field, assuming the spacecraft also has an electric field instrument or electric field antennas, which any wave instrument is basically guaranteed to have electric antennas. The search coils is sort of an add-on. And we also could help determine the wave modes and the plasma and electron density from this. And there's actually 2 papers that have just been submitted with the Juno data, Jupiter, using these techniques and the measurements to determine both the electron and plasma density and the different wave modes that we observe at Jupiter. And we can determine the propagation parameters of the waves, especially when we have 3-axis measurements, the wave normal angle and the pointing vector. And this is just an example I like to show from lightning whistler at the Earth. On the right's a little sketch that Don Garnett created years ago. But basically, you have a lightning stroke. Part of that radio energy from the lightning stroke propagates into space, produces a lightning whistler, which many of you have probably heard before, but has a characteristic dispersion shape. The high frequencies get to the spacecraft first, and then the low frequencies. But in certain cases, this wave can actually bounce between the ionosphere of the Earth. Sorry about that. And so on the top panel is the spectrogram from the search coils on Van Allen probes. The next panel is the wave normal angle. But the bottom panel shows the pointing vector, basically jumping between 0 and 180, which is the direction along the magnetic field line. So basically, the lightning is first detected by Van Allen probes, and then it's bounced back from the other hemisphere, and just keeps coming back and forth over the spacecraft, being more and more dispersed as it propagates. And from the shape of these waves, you can actually determine the density along the path the Whistler propagated along. This is again from Don Garnett's 1998 book chapter, but just showing some of the plasma waves at the Earth that we detect with magnetic wave antennas. And there are 2 main types, and I'll talk a little bit more about this shortly, but search coil antennas and loop antennas. But all the way from ion cyclotron or even Alfvén waves, depending on where you're at in the Earth's magnetosphere, up through continuum radiation, or auroral kilometric radiation, some of the types of waves. And he plots sort of typical noise floors for a search coil and a loop antenna. And from this plot, you can see that loop antennas tend to be better at high frequencies, while search coils tend to be better at low frequency, though that's not an absolute. It depends a lot on the design of your sensors. He also, in his book chapter, had 2 nice little sketches of just the basics of a loop antenna, which tends to be a single turn of wire, quite often, roughly 1 meter in size, or roughly what the polar one was we built, hooked to a transformer, which is then hooked to the amplifier, which then goes to the wave receiver in the spacecraft. While a search coil is usually a mu metal rod of some type of high permeability rod with thousands of turns of wire wrapped around it, hooked to an amplifier, which again goes to the wave receiver. In this sketch here, he shows a flux feedback system where you have a couple turns of a feedback winding, and that's used to flatten the frequency response of the coil or the sensor, which we quite often do now in sensors. And there's a couple of different ways you can do that, which I'll talk about here shortly. This again from his paper, his book chapter, just showing the typical voltage response of a search coil and the loop. Because of the transform, the loop is not as sensitive at the lower frequencies, say roughly below 100 hertz. While the search coil can go down to a few hertz and still get good voltage response. And this is a case where we've shown the frequency response has been a feedback system to flatten the response. Now, why search coils? There's a number of reasons, but one of the big reasons is the relatively small size and low mass. They can range from fitting on a Cubesat up to the Van Allen probe one, and the polar ones we built here were 40 centimeter long sensors, pretty large. And you can get full 3-axis measurements in a reasonably small package, which is often hard to do with the 3-axis electric field measurements, primarily because it's hard to do the actual, the spin plane, the spin axis on a spinning spacecraft to get a long antenna. So you get reduced sensitivity in that axis. You can get really good sensitivity with electric antennas on a spinning spacecraft in the spin plane because you can use long wire booms. But that third axis is often hard to do. But on a search coil, it's relatively easy to do. The reasonably low mass, they ranged from about 100 grams to 2 kilograms. And the 2 kilograms was the Van Allen Pros one. And a lot of that was for radiation shielding. The housing was extra thick to help protect it from the radiation belts. And just an example of the relatively low mass, especially for non-spinning spacecraft like Cassini and Juno, the Cassini electric antenna system that we flew was over 20 kilograms, while the Cassini search coils was only about 1.3 kilograms. And for the Juno, which we have a single electric antenna and a single search coil, the antenna elements was about 2.3 kilograms, while the search coil was only about 0.22, the search coil sensor. So for a lot less mass, you can still get wave measurements. The relatively low power, 10 to a few hundred milliwatts, they cover a decent frequency range. Search coils typically go from a few hertz up to tens of kilohertz, but there's also designs that can measure in the hundreds of kilohertz or even the megahertz. And they have good sensitivity and dynamic range. And you can easily tail them for your specific mission requirements. Now, the last week's great fluxgate talk, one of the questions was, what's the difference of why fluxgates versus search coils? So I added a couple slides to talk about that a little bit. Both fluxgates and search coils sense the local magnetic field through the electromagnetic force induced by a changing magnetic flux in the coil of wire of, say, N turns, A area, and effect relative permeability. And I stole this equation from a paper from Miles 2018, just because it nicely shows that, well, you can have a voltage induced by a changing magnetic field. If you change the area of the loop, you can get a voltage out, or if you change the permeability. And to first order, the search coil measures by the changing magnetic field, the DHDT. And you can't measure a DC magnetic field with the search coil unless the spacecraft is spinning or moving through that field, because you have to have that changing field. But a fluxgate measures the voltage primarily through the changing saturation of the ferromagnetic core. You're basically changing the permeability of the core. And that's why a fluxgate can measure the DC field. And looking at the noise floor or the sensitivity of the two types of sensor, and this is from the MMS instrument paper and the Solar Probe instrument paper, the green line is the fluxgate and the blue line is the search coil on MMS. So basically below about 8 or 10 hertz, the fluxgate is more sensitive. It can measure weaker fields, wave fields. But above 8 or 10 hertz, then the search coil is more sensitive. And this is all, you can see basically the same thing with Solar Probe. Below 8 or 10 or a few hertz, the fluxgate is more sensitive, but at higher frequency, the search coil is much sensitive, so you can pick up much weaker waves. And this is why on any spacecraft that you're interested in measuring waves, it's very good to have both the fluxgate, because you want the DC field, plus it's extra sensitive to the low frequency waves, and then a search coil to measure the higher frequency waves. Now, a little history of search coils in space, or even wave magnetic sensors, antennas. The first space-based search coil that I know of is Pioneer 1, which was launched in October of '58. I believe the first magnetometer flown on space was Sputnik 3, which flew a fluxgate magnetometer in May of '58. But the Pioneer search coil was designed to measure up to a few hertz. It had 30,000 turns of 44 wire on a nickel alloy core, and this is actually a picture of it on the right. And it used the spin of the spacecraft to determine the magnetic field. And it was designed to investigate the magnetic field of the Earth, the moon, if there was any, and the interplanetary space between the Earth and the moon. And a very similar design also flew on Pioneer 5 and Explorer 6. The first higher frequency or VLF space magnetometer was on Engine 3, launched in December of '62, and it was a loop magnetometer designed by Don Gurnett. And this is a picture of it on the right here. It was designed to measure up from about 500 hertz up to 7 kilohertz, and he was interested in measuring the low frequency electromagnetic waves in space. And this is actually one of the images from his paper showing the chorus emissions he detected in their burst data. Now, I should mention the first VLF receiver specifically designed to measure VLF waves in space was launched on the Canadian spacecraft Alio-1 a few months earlier in September, but it only had an electric dipole antenna. It didn't have any magnetic antennas. And since that early, the Engine 3 instrument with Don Gurnett, the University of Iowa has flown a number of different magnetic search coils and loop antennas. Early on, it was all loops, and then since then, it's primarily been search coils with a loop also on DE to measure the higher frequency and then on polar. The ones on the right are the ones I've been involved with, starting with wind and polar in the 90s, and most recently with the Van Allen probes and the Juno instrument at Jupiter, which is still operating. And then we're working on the Tracers one currently, and I've delivered the Viper sounding rocket that's supposed to be launched next in May. The first higher frequency search coil flown in space was on OGO-1 in the early 60s. And I included a picture of OGO-1, a drawing of OGO-1 on the left, because I don't think I've ever seen a spacecraft with more booms on it. And I'm really impressed that they were able to put all those on, and I think the majority of them actually worked, at least on the different, I think they flew 6 different OGOs. It's a really complicated spacecraft, at least it looks like to me. And the other interesting thing about OGO-1 is I discovered in my research when I was looking at it, a hobby of mine is sort of try to read these old instrument papers to learn about these early days of these magnetic antennas. OGO-1 actually re-entered the atmosphere last summer on the August 29th, and they captured a couple pictures of it burning up as it re-entered. On the left is some pictures of OGO search coils. In this paper that discusses them, they basically say they had 4 different designs they used on the OGO missions, but they all had 1,000 turns of wire, a 47 wire on a 27 centimeter core, nickel iron core. The resonant frequency was about 700 hertz, and the sensors weighed about 150 grams, and they were on a 20-foot boom. And this is a picture of one of the from OGO 2 and 4. This is one of the sensors up on the top left, and the electronics package for OGO F, the preamplifier assembly. And this is some of the data from OGO-1. I believe this was OGO-1. And when they crossed the bow shock crossings, where you can see the Earth's magnetic field or turbulence, and then the solar wind magnetic field is much quieter. And part of my little hobby is I've tried to collect a list of every spacecraft that has had a magnetic antenna on it. And this is a list I've come up with today. This is the Earth ones, and then the next slide will be the planetary and solar wind missions. So if you know of a mission, I apologize. I would love to hear about it. So send me an email if you know of a mission I missed or thing. And I know there are a couple of upcoming ones, including some Cubesats, and like the Jewish mission to Jupiter have search coils on it. These are the planetary and solar mission ones from starting with Helios up through Mercury Magnetospheric Orbiter or Bepi-Colombo. Now, the basic design of a search coil, like I mentioned earlier, is thousands of turns of wire wrapped around a high permeability core hooked to an amplifier, and which then goes to a wave instrument of some type. And on the right is actually a sketch or a drawing of the polar search coil that we designed here. Again, the high permeability core, it was 40 centimeters long. For the polar design, we had 2 bobbins. so we could increase the number of turns without increasing the resonant frequency, and the preamplifier fit in this middle section. And for the polar and wind search coils, each search coil was its own individual unit, and they were mounted individually on the end of the boom. This is a picture of the Van Allen, early Van Allen prototype. Again, the 40-centimeter core. We've wrapped the bobbin here in some copper tape for an electrostatic shield, because you can pick up electric fields if you don't have an electrostatic shield over the coils. This on the bottom right is the Juno search coil sensor. The wheels on the end were actually are there to hold the thermal blanket over it when it was mounted to the spacecraft. We recently, a few years ago, got our own winding machine here, or an updated winding machine. We had an old homemade one that was very labor intensive, but now we can easily wind our own bobbins, try different configurations and different number of turns as we're testing and designing different search coils for different mission parameters. The search coil works due to Faraday's and Lenz's law of magnetic inductions. And this is an equivalent circuit for an open search coil sensor or a voltage sensor. You have the resistance of the wire, the inductance of the coil capacitance, and quite often we add a damping resistor, which helps damp out the resonance peak. And if you solve for this, you basically get the voltage out of this circuit here depends on the resistance, the capacitance, and the inductance. And in fact, there's a resonant frequency that's basically 1 over the square root of the inductance and the capacitance. On the right is the actually transfer function of that output voltage for input nanotesla for the wind search coil from 1992. The solid line is the theoretical equation here for the measured values of inductance, resistance, etc. And the dots are what we actually measured out of that search coil. So you can see this theory works quite well. One thing to notice here, though, is with a search coil like this, the voltage out depends on frequency. So at 100 hertz, you're getting about 0.02 or 0.03 volts out for 1 nanotesla in. But at a kilohertz, you're getting 0.4 volts out roughly. And so if you're hooked to a sweep frequency receiver or a multi-channel analyzer for your wave instruments, and you're only looking at the data in the frequency domain, it doesn't really matter because you can easily calibrate out this difference in frequency. But if you have burst data and you're looking at the waveforms of the data, that actually makes it more difficult to calibrate that waveform if you wanted to look at calibrated to know actually what the nanotesla was at the different frequencies. Because if you have a wave at 100 hertz, 100 hertz and a kilohertz present in the same waveform, it's going to be dominated in the same nanotesla field originally producing those signals. That 1 kilohertz signal is going to be dominating that waveform. And so quite often in later designs, people have applied some type of flux feedback to these design to flatten that frequency response. And one way to do that is use a voltage amplifier and a flux feedback coil with a few turns wrapped around the coil to basically flatten the frequency response. And both Geotel and Demeter use this method, and other spacecraft have too. And this is from the Demeter instrument paper, where basically instead of having a peak here, you have a flat region which was the region of interest they were they were trying to measure the primary science they were doing. Another way to do this, and most recent search coils have used this technique because current op amps have gotten much quieter with time, is to employ a current amplifier or feedback. Basically, you're measuring the current from the coil to produce the voltage that goes to the wave instrument. And the Van Allen, Juno, and the Arasi search coils all use this, including many others. And this is a sample circuit from a Osaki paper from 2014. But this shows the response from the Juno search coil. So basically from 100 hertz up to 10 kilohertz, it's flat over frequency. And so if you're measuring waves in this frequency, you can actually easily compare in the time domain, a 100 hertz signal to a 5 kilohertz signal. You don't have to try to do like do an FFT, do a calibration and reverse FFT to try to calibrate the waveform. And I'll talk a little bit more about that when I get to some of the science examples. Quite often we compare search coils from different missions by their noise floor, but we really shouldn't necessarily do that because every mission is different. Every mission is trying to measure different types of waves or have different science requirements. And so when we design the search coil to meet those requirements, Sometimes we want to, make as sensitive as a sensor as possible so we can measure the weakest waves. But other times we have to worry about measuring really strong waves. So we want to make sure we make a sensor that isn't going to clip when we measure the typical strong waves in the environment. So this is just one way you can compare search coils. But again, just because one doesn't measure as sensitive as another, it doesn't mean it's not a great sensor. It just means it was designed to measure different things for that mission. And some of the things we worry about is the mass and size allocation, especially the core length for the tracers mission, for example. We in the design phase, we had to fit inside the fairing that we might use to launch the mission. And so we had to have shorter cores so they would fit within the spacecraft envelope. Whatever frequency range you expect to measure, you want to optimize your sensor to measure that frequency range. Again, the dynamic range, I already mentioned that you want to be able to measure the maximum signals you want to see and the weakest signals that you expect to see. How many axes can you have? 3 axis is best, but sometimes due to mission restraints, you can only have 1 axis. The type of wave receiver you're going to go into, the power available, the telemetry, and the radiation environment, all the things we worry about when we design sensors. And if you're interested in search coils, I strongly encourage you to read actually all these papers. And there's actually a number of books out there too that talk about different magnetic sensors. And I've listed some that I found very useful. And a lot of these books also have chapters on fluxgates and even more exotic types of sensors. And some recent variations that people have done, especially Coil from France, they have these basically these dual frequency sensors where they have a winding that measures the low frequency range, and then they have a higher frequency winding that can measure up in the hundreds of kilohertz with good sensitivity. And this is a way to not needing to fly a large loop antenna. You can actually get good measurements using your search coils and keep your mass and size small. They've also done some work with these interesting cubic sensor diagram. This is a drawing of one, which is a very interesting paper from 2014. And then they've also investigated some optimized core shapes where they have these, basically they call them magnetic concentrators on the end, which increases the permeability of the core for a certain size core, which improves your sensitivity. David Miles here at Iowa, and actually before he even came to Iowa, has been working on these hybrid magnetometers, which basically combines a flux gate with using a racetrack core and a search coil. The reason we're investigating this is, on a large spacecraft like Van Allen probes, you can have 2 booms where you have the search coil on one side and the flux gate on the other. Actually, the search coil is over here and the flux gate's over here. But on a small sat like a Cubesat, it's very difficult to have 2 booms. It's even difficult to have 1 boom quite often. So if you could have on a small sat, if you could combine a flux gate and a search coil in a single package, it would allow you to have both measurements on a small sat without worrying about trying to keep them far apart from each other, because there can be some interference issues doing. Of course, because there's interference issues, combining the 2 is difficult. This is a picture from his 2018 paper where he just did a simple search coil, a flux gate, racetrack core, and this is your typical racetrack. A typical flux gate core tends to be these ring coils, and this is a typical core of the search coil. And we've been doing some measurement or some modifications here, trying to develop a hybrid magnetometer. And a number of people have been working on Cubesat size search coils. And in fact, this is one, a 3D laser printed model we built. We've done some work on a Cubesat one, and we had a proposal in that we failed at, but the search coil, we did a single axis testing one, and it actually performs much better than I ever expected. And I could actually build you a very good Cubesat size search coil if you wanted me to. But Canvas with Bob Marshall, the PI at the University of Colorado, this was from a press release and a website they have here. They have a Cubesat which has a search coil that's going to be on a 1 meter boom that deploys out. That's supposed to launch in 2022. I'm not sure if that schedule's still on schedule for that, but this might be one of the first Cubesats that will attempt to fly a search coil magnetometer. And I'm sure there are others. Again, I'm not up on all the search coils. There's so many being developed currently. So I welcome if you know of one or if you're building one, I would love to hear about it. When we test search coils on the ground, we have a number of issues. And the biggest issue is 60 hertz in the US and 50 hertz if you're in Europe, background signals in your lab. Basically, you have to figure out ways to, if you want to measure your real signals or calibrate it, how you remove these 60 hertz signals. And there's also other interference sources quite often in the lab. I moved to a new lab in the building, and the fluorescent lights in that room produce a really strong signal of 48 kilohertz. So basically, whenever I'm trying to test my search coils, especially looking at the noise floor of them, I basically turn all the lights off in the lab. And I also just discovered 2 weeks ago that Dr. Miles is in the lab directly below mine, and he has a really nice calibration system with these large coils. But when he's calibrating his flux gates, especially 11 hertz, I can see that in my search coils really well. And so we basically have to timeshare that he can't run his coils and I'm trying to do certain tests in the lab. But to mitigate these external noise sources, we use mu metal cans. And this is actually a picture of the Van Allen Probes mu metal cans we built or bought. These are large square cans, and this is actually the Van Allen Probe search coils in the middle of it. And we added some drive coils inside, and there's lids. But basically, we put the lids on that reduces the lab background fields, and we can drive signals in at a kilohertz or whatever of known strength to test the search coils and make sure they're still operating. We also use various transmitting loops at times to do specific tests, and I'll show a picture of one of those in a second. We quite often, we have solenoid-shaped mu metal cans or cylinder-shaped mu metal cans. We have solenoid drive coils because for those you can create well-behaved magnetic fields inside of the solenoid so you can do good, accurate calibrations of the sensors. And these are just some pictures. These are some mu metal, the cylinder cans. This is the Van Allen Probes square can we have, and this is one of the transmitting loops, which has two perpendicular loop antennas, and basically we can drive them 90 degrees out of phase to produce a rotating magnetic field at the sensor. And it allows us to basically to make sure we have no sign errors because we're sort of can very easily have 180 degree phase shifts if we flip a cable or something. And so this is a test we do at the end of our, hopefully when it's mounted to the spacecraft with all the flight cables to make sure we have all our minus signs correct before we try to do things like wave propagation analysis. This is just an example of 60 hertz interference. This is on the ground inside the mu metal can. Even we saw the strong 60 hertz signal. Actually, this specific spectrogram was when it was on the rocket at the Cape Canaveral a week or so before launch. And there's a strong 60 hertz signal. And this is actually a signal after launch in space. So you can see all these low frequency signals disappeared because they were all produced from ground interference. And this is an example from a test from an early Bepi-Colombo search coil prototype from Coil 2007 paper showing he's seeing harmonics of 50 hertz. Actually, this is 150 hertz here, and then 200 and 250, etc. It's sort of interesting they don't see the 50 hertz harmonics, but quite often the third harmonic is the one we see the strongest, either 50 or 100 hertz if you're in Europe or 180 hertz if you're in the US. We also worry about the spacecraft being magnetically clean. Both the fluxgate and the search coils worry about this, and it's primarily because we're so sensitive. We can pick up such weak signals. And there are a number of, the first thing you should ever do if you're on a spacecraft is convince them to use good design principles. And this does not have to be expensive. They just have to be, think about these as you're designing your instruments or your systems. Don't have large current loops or any types of current loops. If you have, when you string your wires, don't create loops. Twist the wires, which helps reduce these loops. If you have solar cells, backwire them. And that's important for both fluxgates and search coils. For search coils especially, choose frequencies outside the science requirements and use common frequencies and choose frequencies as high as possible. If you have to choose an oscillator for your circuits, pick a high frequency and have everybody for their power supplies pick 50 kilohertz or harmonics, 50 kilohertz or 100 kilohertz. It can make a huge difference on how quiet your spacecraft is. We also quite often try to mount our search coils on booms as far from the spacecraft as possible, because if there is any noise that sneaks through on the spacecraft, if you're far away from it, you don't measure it because it drops off as either 1 over r squared or 1 over r cubed, depending on what kind of signal it is. It's also good to test your subsystems early if possible. On many missions, we have provided the spacecraft team a sniffer search coil, just a simple search coil that they can hook up to an oscilloscope or a spectrum analyzer to, wave around their system as it's running to see if it produces noise early on. So that maybe they can try to either, redesign or relay out a cable or even add some shielding. And then on orbit, if you have things on the spacecraft that produces noise, we schedule things not in the region of prime science interest, or sometimes we duty cycle the different instruments or something on the spacecraft so we don't interfere when we're trying to get our prime science measurements. These are just some pictures of booms. This is the Van Allen probe boom with the search coil on the end of it. This is it mounted up against the spacecraft. And as you can see, for the Van Allen probes, the way they mounted it, so part of the search coil stuck over the spacecraft, so the other part didn't stick out too far, and would have to worry about hitting the spacecraft fairing that it would sit in. This is just a drawing drawing or painting of the Van Allen probes and deployed in space, and it's a nice design because they actually use the solar panel, hook the boom to the solar panel to get the sensor even farther from the spacecraft. So I don't remember the exact distance here, but it was 6 or 8 meters out from the spacecraft. And we actually like to be on when they deploy the booms if possible, just so we can see how the noise changes. And this is actually an example. This is before that boom was deployed. You can see we're seeing some interference signals, and the boom was deployed, and then we basically just saw the background signals from natural signals. This is a plasmapheric hiss. And it just shows you, the difference having a boom and not a boom on the spacecraft, the difference it made. This is just a drawing of the polar spacecraft. It had astromass boom. The search coil is actually, the spin axis boom was mounted to the end of the boom and the loop antenna. And then there was a little extra boom that folded out another foot or two with the 2 spin plane axis search coils. And the fluxgate was on the other side of the spacecraft. For Cassini, because it was not a spinning spacecraft, we couldn't have long booms, but we did have a 1 meter little rigid boom here that the search coil is mounted to. And this is a picture of the search coil magnetometer for Cassini. The Cassini spacecraft was reasonably quiet, but the one signal we did pick up was the reaction wheels. It had basically gyroscopes on it to help point the spacecraft to control the pointing. And we actually knew we were going to see these before launch. This was a test on the ground where we saw they were spinning the one reaction wheel at different speeds, and we could see the a line show up in our spectrograms from that. This was from a test they did in orbit, in flight, where they basically spun the wheels up to a certain frequency, and then they turned them off to see how long it took to spin down. And so you could see they spun them up, turned it off, and they dropped in frequency as they slowed down. And this was an example. We saw this down in the tens of hertz on Cassini, up to slightly above 100 hertz. Basically, and it was due to the magnetic moment of the wheels. But depending on how the spacecraft is pointing, this frequency changed because they spun different wheels at different frequencies. And here they were doing a slow roll where they were spinning one wheel up in speed and down in speed, and we saw this sawtooth. For the Juno spacecraft, we just had a single axis antenna, which we mounted in the spin plane spacecraft, and it was actually body mounted. We weren't able to have a boom due to a number of limitations. And here it's underneath the thermal blanket. But the Juno spacecraft spent a lot of effort to create a quiet spacecraft, and basically it succeeded. Even though we don't have a boom, this is data in the solar wind before we got to Jupiter, where we don't really see any signals from the spacecraft during this period. Now, there are some things like when they go run the thruster, they turn an IMU unit on, and we do see a line around 1 kilohertz when it's running, but they only run that for short times when they're doing a engine burn. But the Juno spacecraft was incredibly quiet, especially considering we have a body-mounted search coil. And then just to end here, I'm going to talk about a little bit some of the science we do. First off, I'm going to show some example from Whistler mode Chorus. And Whistler mode Chorus is an intense, highly structured magnetospheric wave emission. made up discrete wave packets, and it's considered a very important source for acceleration of electrons to relativistic energies in the Van Allen radiation belts of the Earth, and also at Jupiter and Saturn. Usually, chorus is made up of rapid cessation of intense ascending tones and frequencies over very short time intervals lasting less than a second. And I'm going to show some examples. And they were actually named because the first people that heard these, and they're in the audio frequency range, they sounded like the dawn chorus of chirping birds. And so they were named the dawn chorus originally. And this is 2 examples from Van Allen probes. On the left, I plotted the spectrogram from the BU sensor. And you can see these rising tones in frequency. This goes from 0 to about 4 kilohertz. The top 3 panels are the electric channels. We have all 6 channels on Van Allen probes, though you can tell the spin axis or the EW antenna is much shorter than the EU and the EV antenna, so its sensitivity is not as good for picking these waves up. And then the 3 search coil channels here. This is another example where you can see the waveform for the BU and the spectrogram from the BU. You can see these individual chorus elements and the wave packets in the search coil data. And what I mentioned earlier that we calibrate this because we flatten the frequency response with our feedback system. Basically, this calibration is good for any waves from about 100 hertz up to 10 kilohertz. And this makes life much easier. Andrei Sanalik analyzed these individual chorus elements, and as it drifted in frequency from slightly, 600 hertz up to 1.5 kilohertz. This is frequency here. And if we hadn't flattened the frequency response, it would have been much more difficult to look at these calibrated waveforms here and understand the differences in these packets. In both the perpendicular and the parallel to the magnetic field amplitude. Also, because we can get the wave propagation parameters if we have 3 axes, Mike Ladakh did with the polar data showed that all the chorus north of the equator was basically propagating away from the equator northward, and the chorus observed southward was propagating southward. And that was able to do from the 3 axes of the polar search coils. And I did the same thing with the Saturn chorus observations of Whistler mode chorus. At Saturn, again, north of the equator is propagating away from the equator. Near the equator, you saw a mixture, magnetic equator, and then southward, it was all propagating southward. And again, that shows that the source of the chorus is near the magnetic equator. And at Jupiter, there's been a number of studies using the search coils, also looking at the chorus at Jupiter. And this is an example of that. And again, I just love this example of the lightning whistlers with Van Allen probe, just because it just so shows the capability when you have 3 axis, high resolution data. You can just see the individual elements, the directions. You can see how the wave normal angle varies, etc. Just all kinds of interesting things you can do. At Jupiter, we only have a single antenna, a single electric antenna, and a single search coil. So we don't have 3 axis. And this is an example of a lightning whistler at Jupiter. We're very close. The orbit of Juno puts the spacecraft very close to the ionosphere. So basically, the majority of the lightning we've detected at Jupiter has come straight out of the ionosphere and straight to the spacecraft. It's not propagated very far, so it has very low dispersion. Though this one does have the high frequency folds over some. And this is the waveform. This is an FFT of this waveform up here. But because the spin axis, the electric antenna is in the spin plane and the search coil antenna is in the axis, the spin axis, the perpendicular, 90 degrees perpendicular to each other. And we can measure the phase difference between the electric signal and the search coil signal. We can actually determine with some assumptions on the wave mode if the wave is propagating up parallel to the field line or anti-parallel. And a number of studies have looked at this for these lightning whistlers and other whistler mode waves we detect. In this case, this lightning whistle is propagating up from the planet just as we expected from the small dispersion, the very short dispersion we see. And so this is something we can do, even though we don't have 3 axes, we can still determine some wave propagation parameters. And so I'm going to end there and try to answer any of your questions. Thank you very much.
Great. Thank you, George. That was very interesting talk. We have a couple of questions here in the chat. I will read them. Sorry for the noise in the back. So the first is from Witten Reeve. So are search coils temperature sensitive? If so, how do you compensate for temperature variations?
They can be, though the design of your amplifier and stuff can mitigate that greatly. The Van Allen and Juno ones that we designed were actually, we tested them from -70 up to +40 or 50, and the amount of both amplitude and phase difference was reasonably minor. So we actually didn't worry about the temperature differences in flight because the calibration did not change enough to affect that. But sometimes some designs are more sensitive than others. We quite often will have a temperature sensor on the search source sensors, and before launch we'll test it at different frequencies and calibrate it at the different frequencies. So if there is a difference that's important for the science you're trying to do, and you track the temperature, you use the -30-degree calibration when it's cold, and you use the +40-degree calibration when it's hot. But we actually haven't had to do that much with the ones we build here.
Okay, thank you. And the next question is from Mark Moldwin. Has anyone recently attempted to extract DC magnetic field from the spinning or orbit motion of a MSC, search coil magnetometer?
Yes, the Pioneer 1 and 5 and Explorer 6, basically did that. They determined the DC field from the spinning spacecraft. More recently, because fluxgates are so much better at doing it, most people don't do it nowadays with the search coil, they fly a fluxgate. But, with Juno, we're on a spinning spacecraft, we actually had, and Jupiter's magnetic field is incredibly strong. So we actually put a low pass filter in the design, a high pass filter in the design to filter out the DC magnetic field, because we were worried about, how large a voltage it was going to put into the signal, into our electronics, due to the spinning spacecraft just from the DC field. So you do have to worry about that, especially if you're in a low altitude spacecraft, how much field that DC, if you're on a spinning spacecraft, is going to put into your electronics.
Okay, thank you. And from our colleague Kyle Murphy, what is the back wiring in the solar cells?
Can you say that again? You broke
okay, what is the back wiring in the solar cells?
You basically run the wires parallel to each other, going in each direction. And so if you produce a field going one way, you counteract it by going the other way, is the way I understand it. And so, if you have a current going this way and a current going this way, and the wires are really close to each other, you sort of cancel out the field they produce because they're producing fields in opposite directions. There's a number of tricks like that that you can do to basically, you're going to produce a field because you put a lot of current through a wire, but you try to counteract it to make it as small as possible, a distance from that wiring.
Okay, thank you. And the next question is from Ulrich. Why do the most search coils measure only up to around 20 kilohertz and not higher, 100 and beyond?
Yeah, it has a lot to do with the capacitance of the wires and the windings thing and the resonant frequency. If you wrap, 100,000 turns of wire, a thin wire in a small area, your resonant frequency tends to be around a kilohertz or something. And so to get to the higher frequency, especially in the older days when we were using voltage preamps instead of the current, you got above the resonant frequency, and then you started running into things did change a lot more with temperature, and it was more sensitive to a lot of things. So it was more, I guess, sort of more stable below at the lower frequency for the number of turns we tended to use to try to get the sensitivity up. It is absolutely true with some of these newer designs, you can go to higher frequency and still get pretty good sensitivity. And the Bepi-Colombo is one example. The Solar Probe one is another where they've added this high frequency curve. And even the Viper search coil we designed to go up to 50 kilohertz with these current op amps can allow it. So I think in the future going forward, you will see some designs that are more optimized for the higher frequency. The other reason is that the Earth, the majority of the plasma waves that we measure are sort of below 20 kilohertz, depending again where you're at in the orbit. But say for the radiation belts, the majority of them are below, I'll say 10 kilohertz even. And so you design your sensor to sort of the waves you're trying to measure. And so, you know, a lot of those waves that people have been interested in are below 20 kilohertz. So the sensors were below 20 kilohertz.
Okay, thank you. And the last question in this chat is from Sergey. There are successful attempts to merge fluxgate and search coil data. Which are the main principles of this merging procedure? And is it always possible to merge DC and AC magnetic field data? Are there any problems?
I guess my answer would be it's probably always possible. It just depends on how big your error bars are. MMS, I know, spent a lot of effort to do this, to sort of cross calibrate between the fluxgate and the search coils. And I know other people have done this too. The issues to worry about is, you know, to make sure you have good ground calibrations before launch. So you have, you know, good calibration, the fluxgate up to the higher frequencies where they overlap, and then, you know, good low frequency calibrations. And sometimes that's hard to do, again, partially because of the interference you quite often see from 60 hertz and other things on the ground. Like for Juno, because we have this high pass filter in our system, we only go down to about 50 hertz, while the fluxgate, depending on exactly how they analyze the data, you know, can sort of go up to that. But we sort of have a gap in the Juno data between the fluxgate and the search coil, but it was designed that way because we were worried about the DC field. But there has been work. Ali Solomon's done a paper where he's looked at magnetic wave emissions from the Io Taurus, where he's combined the fluxgate measurements, power spectrum to the search coil, and they line up well. They just have a gap between them because there's not exactly a frequency overlap. So you absolutely can combine the two measurements. There's a number of things you have to watch out for when you do it. And again, it partially also depends on what type of measurement you know, are you just worried about the amplitude, or you're trying to look at the phase, you know, difference between the two different instruments and stuff like that. It's similar to, you know, particle instruments, high energy particles and low particle instruments try to, you know, intercalibrate regions they overlap. And there's lots of times just little issues you have to work out to make sure everything's done correctly. And you have the calibration data to actually be able to make sure you understand the two different differences in the instruments.
Okay. So does anyone else have a question? We still have time. If you don't want to type, just open your mic. Well, I don't think so. Everything is cleared. It was a great talk. Thank you again, George.
Thank you very much for having me.
So
appreciate the opportunity to give the talk.
Thank you too.
If anybody's interested in me building search coils for them, just let me know.
Yes, we have your presentation and we have your contact. Let me see. The last thing is, we have a 2-week break, and we will resume on April 19 with Harold Frey, and he will discuss about optical instruments. So yeah, thank you everyone. Thank you for attending today, and I hope see you all in 2 weeks time. Thank you. Have a good week.
Thanks, George.
Thanks.